Lesson 19, Mechanical Waves. There are two basic ways to transmit or move energy from one place to another. First, one can move an object from one location to another through kinetic energy. Second, one can move energy in the form of waves. Waves are energy carriers moving energy through distances as the result of vibratory motions. Examples of waves are seen or heard around us every day: ripples on water, sound, sunlight. There are two general classes of waves: electromagnetic waves and mechanical waves. Electromagnetic waves, also known as light, are capable of moving through objects or through the vacuum of space. We will study electromagnetic waves and light in Physics 30. Mechanical waves, on the other hand, require a medium of some kind, such as water, air, string, a spring, metals, rocks. Mechanical waves require molecules to vibrate so that they can travel. So they require a medium through which they can travel. Mechanical waves cannot travel through vacuum since there is no substance available to support and maintain the wave energy. Mechanical waves require particles to actually be transmitted. They cause the particles to vibrate. There are no particles in space. That's the definition of a vacuum. Therefore, there can't be any mechanical waves in space. There are two types or classes of mechanical waves: transverse waves and longitudinal waves. For transverse waves, the particle in the medium vibrate perpendicular to the direction of motion of the wave energy. A transverse wave has crests, which have positive amplitude, and troughs, which have negative amplitude, as shown in the diagram below. You can see, even though the wave is moving horizontally, the particles of the wave are traveling up and down perpendicular to its motion. For longitudinal waves, which are also called compression waves and pressure waves, the particles in the medium vibrate parallel to the direction of motion of the wave energy. The wave travels by causing instantaneous compressions and refractions in the medium. A compression is a region where the particles are instantaneously more highly concentrated, and a refraction is a region where the particles are instantaneously further apart. Of course, once the wave passes through a given region, there is no trace of the wave left behind. Here's our two types of waves again. A transverse wave is perpendicular to the direction of motion. Longitudinal wave travels along the wavelength so that it's traveling parallel or in the same direction as the direction of motion. Wave pulses and waves. A wave pulse is a disturbance that has a beginning and an end. The word wave or wave train is usually reserved for a continuous series of pulses. A single wave pulse travels along the medium as a single amplitude. The amplitude of a wave pulse, or a wave, is the maximum displacement of the medium from the equilibrium position. The equilibrium position is the position that the medium rests at, and the maximum amplitude, or just the amplitude, is the maximum height. Wavelength, period, and frequency. For any type or class of wave, the wavelength, which is symbolized by Greek letter lambda, which sort of looks like an upside-down pitchfork, of a wave is equal to the distance, measured in meters, between 2 points which are in the exact same phase or position on the wave. So if you can find 2 points where the wave repeats itself, the distance between those 2 points is the wavelength. I've drawn some examples of how to measure wavelength on the wave in the diagram. The maximum positive amplitude of the wave is called a peak. The maximum negative amplitude of the wave is called a trough. The period is the time it takes for the wave to travel one wavelength, and the frequency is the number of pulses or vibrations that occur in 1 second. The unit for period is usually seconds, and the unit for frequency is hertz. As we saw in circular motion, the relationship between period and frequency is given by period equals 1 over frequency, and frequency is equal to 1 over period. As the period of a wave increases, more wave fronts pass a single point in a given amount of time. So you can see a higher frequency wave is a lot more compact. There's a lot more wavelengths contained in an amount of space, so that more wave fronts will pass by in a given amount of time. Speed and the universal wave equation. All waves move through different materials, or media, which is plural for medium, with different certain speed. The magnitude of the speed will depend on a number of factors. For example, sound waves travel through rocks faster than they travel through air, since rock has a greater density than air. Another factor is rigidity. The more rigid the medium, the faster the speed of wave in that medium. For all waves, there is a single relation between speed, frequency, and wavelength. This is called the universal wave equation. From our previous work, we know that speed is given by v equals d over t. For a wave, the distance traveled in one cycle is a wavelength, and the time required for one cycle is the period. Thus, the velocity of the wave is given by the wavelength divided by the period, or since f equals 1 over the period, which tells us the velocity of a wave is given by the wavelength times the frequency. This is called the universal wave equation because it applies to all kinds of waves. For example, a series of waves with a wavelength of 2.5 meters have a frequency of 50 Hz. What is the speed of the wave series? For example, a series of waves with a wavelength of 2.5 meters has a frequency of 50 Hz. What is the speed of the wave series? We use the universal wave equation, which is v equals f lambda, to determine the speed of the wave. This is 50 Hz times the wavelength of 2.5 meters, which gives us 125 meters per second, which is the speed of the crest of the wave as it travels through the medium. A wave series with a wavelength of 10 meters has a speed of 300 meters per second. What is the frequency of the waves? In this example, we use the universal wave equation, but we rearrange it for frequency. Frequency is equal to the speed of the wave divided by the wavelength. So this is 300 meters per second divided by the 10-meter wavelength, which gives us a frequency of 30 Hz. Next, we're going to look at a series of properties of mechanical waves. The first of these is reflection. When a wave or a pulse on a string or rope meets a boundary of some kind, some or all of the wave energy will be reflected back by the boundary. The manner in which the wave is reflected depends on the nature of the boundary. If the wave boundary is a fixed end, the reflected pulse will be inverted relative to the incident pulse. It will come back upside down. If the boundary involves a free end, the reflected pulse will be upright relative to the incident pulse. The reflected pulse will be the same way up as the pulse that hit. Refraction. Refraction occurs when a wave changes from one medium to another. This could be going from a heavy string to a lighter string, or a heavy chain to a lighter chain, or moving from one temperature of water to another temperature of water. When a wave refracts, the speed and the wavelength change, but the frequency and period of the wave remain the same. When a wave pulse moves from one rope to another, some of the wave energy is reflected. We call this a partial reflection, and some is transmitted to the next rope. For a wave traveling from a slow medium to fast, the reflected pulse will be upright. This means that it will travel back the same way that it hit the boundary with. For a fast medium to slow, the reflected pulse will be inverted, just like if it was attached to a fixed end. Another property of waves is interference. When two waves moving in opposite directions meet, they do not reflect off each other. Rather, they pass through one another. As they do so, the waves superimpose and interfere with each other, creating a temporary waveform that is the sum of the two waves. If the waves meet in phase, we call this crest to crest or trough to trough, or in other words, they meet when they're both pointing the same way, then the sum of the amplitudes of the wave produces a larger waveform. This is called constructive interference. On the other hand, if the waves meet out of phase, crest to trough, and trough to crest, the sum of the amplitudes tend to cancel each other out, resulting in destructive interference. Standing waves are a special case of interference. The amplitude and wavelength of interfering waves are often different, and that's when you see interesting patterns of constructive and destructive interference. But waves with the same amplitude and wavelength traveling in opposite directions result in an interesting interference pattern called a standing wave interference pattern, or simply a standing wave. In the animation I'm about to show you, we have two waves traveling through the same medium. The red wave is traveling through the medium to the right. The green wave is traveling through the same medium to the left. The red and the green waves both have the same wavelength, amplitude, and frequency, but they're traveling in different directions. When these two waves combine and interfere with each other, they produce the blue wave, which is a special kind of wave called a standing wave. In the animation you can see the times when the green wave and the red wave meet. The blue wave, or the produced resulting wave, hits a peak. When the green wave and the red wave are completely opposite of each other, they completely cancel each other out, and the blue wave disappears for a moment. The blue wave is what we call the standing wave, and you can see on a standing wave, there are points that don't seem to move at all. These points are called the nodes. There are also points that are always the maximum or the minimum amplitude and just flip up and down. These are called the antinodes. Standing waves are commonly seen in music and in sound. When you pluck a guitar string, the wave in the guitar string travels up and down the string, gets reflected back, and interferes with itself, producing standing waves that have particular frequencies that are pleasant to hear. Standing waves can occur in many different patterns. You can see you can have a standing wave with only one antinode, or if you increase the frequency by adding a little more energy to the wave, you can have two antinodes in the same length of string. You could have three antinodes if you increase the energy again or wiggle the string a little bit more. Four, 5, or 6. The faster the two waves are traveling through the medium, the more nodes and antinodes you're going to get in your standing wave. Again, maybe on a still diagram this time so you can fully see it. The sections of the wave that always remain at the equilibrium position are called the nodes. The section of the wave that are always at a maximum or minimum position are called the antinodes.